Okay, here we are for lecture 5. It's slightly more interesting than the past 2 weeks. And we're going to start learning some things that you could put on some drawings. I gotta be honest, so far things have been pretty easy for you guys. Starting next week, things are really gonna start to pick up the pace. We're gonna start to be getting into more math. This week, we're using sizing guidelines. You might hear people refer to them as rules of thumb. That's what most engineers call them. That's what kind of the industry calls them. One year, I had students write in the review that I supported domestic abuse because I called them rules of thumb, because they had heard that meant something very explicit. That is not true. It's an urban legend that is not substantiated in fact in any way. That said, rather than deal with that, I can tell you it made me cry. Rather than deal with that every year, I decided to just call them sizing guidelines. The difficulty is that you're going to hear everyone else in the entire industry call them rules of thumb. So I can't just gloss over the fact that they're actually called rules of thumb because that's what everyone else calls them. But we will refer to them as sizing guidelines here. So there's a little bit of math to it, but it's not much. And I was going to do it by recording on my phone, my calculations. I'm a little bit worried we're going to lose momentum if I do it that way. So I'm going to go through all the lectures. I'm going to go through the whole lecture. And if we need to, I will then go through the examples a second time, recording it while I write it out by hand. I have some solutions, I think, in the works on how I might modify or update that. The main one being, I think I might order an external webcam that's on a much more flexible mount, that I can have it recording me, and then when I need to do a hand calculation, turn it and tip it down so that it can record my hand calculation, and then turn it back up and tip it to me. And that way you'd also always see the lecture slides even during examples. I have a line on one. I just have to kind of order it and figure that out. So what the idea of the sizing guidelines today is this would let you put something on your drawings at the preliminary stage, or maybe even design development. It's probably what the engineer would do at a design development stage as well. More just a quick review of the drawings, knowing how long they are, or how long each member is, giving a preliminary size as a placeholder. We need them to be right-ish, close to right, because we want to make sure we have enough ceiling space to fit our members in, and enough wall space to fit our columns in. If we go about this wrong, there's no implication, there's no life safety, because it gets designed in the end. The problem is you could have a pissed off owner. You could end up having situations where if you didn't allow for enough ceiling depth and you had a maximum cap on the height of your building, if each ceiling system needed to be twice the size, maybe you lose a whole floor on your building. And if your client is renting that building out or selling retail space, they've just lost a huge amount of income from that property that they had counted on based on the preliminary design. So this doesn't need to be perfect, but you need to have an understanding of where it's coming from. And you need to have an understanding of when it might not be the best thing to give you your preliminary size. So they're broadly accurate guides or a principle based on experience or practice rather than theory. So this isn't math. This is, we've done it enough that we know that they tend to be about this deep. Now, most of the time, we're talking about the length of a member relative to how deep it is, or from the top to the bottom of it. If we're talking about a column, we're talking about the smallest side of our column. So this will give you an approximate depth of a beam or of a column dimension. Everything you need to know about structures, you already know. I've said this several times. These rules are basically based on that gut feel. So remember that gut feel. If you look at the system and it looks too small, it's probably because it is. It's because you have some understanding that there's something going on there that means that element should be bigger. And we'll talk about some of those examples as we go through this. So how do we use structural sizing guidelines? We're saying there's a linear relationship between depth and length. So how deep it is and how long it is. I can tell you that that's absolute bull crap. And next term, we're going to actually prove how not true that is. That is a complete and utter fabrication. But it's pretty good in the normal range of things for an estimate of what our size might need to be. We're going to calculate next term that it's not a linear relationship between depth and length. But for our sizing guidelines, it lets us put something on with very quick calculations without having to go through in-depth structural analysis. The idea here is that if you know the length of your member or your beam, you will be given a rule of thumb or a sizing guideline. You'll see me often write ROT as a placeholder. You'll be given a rule of thumb sizing guideline that you take the length, divide it by your sizing guideline, and it tells you the approximate depth that would be good for that beam as a placeholder. That means you can rearrange that. If you know that you have a maximum ceiling height that you can fit your beam into, well, you can figure out what the maximum length your beam could possibly be based on very preliminary information. Width, that's the height of the element divided by the sizing guideline. So this would be for columns and walls. And thinking about it in the opposite, if you know what the width is, so if you knew that you could only have 290 block wall, you could multiply it by your sizing guideline and figure out the maximum height that that thing could be. So if you've picked how long the member is based on your layout, you can estimate how deep it needs to be. If you know how deep your member can be because you have a limited ceiling height, you can estimate how long it can be. So when can you use your sizing guidelines? Well, they'll be close to the final design member when they're within the range of normal applications. So this assumes things are relatively standard, that if you're talking about a steel building, you're talking about a relatively normal steel building. If you're talking about a wood house, you're talking about a relatively normal wood house. If you're talking about a concrete building, you're talking about a relatively normal condo or office building. These might not be the estimates for you if you have really large loads. If you're spanning extra long distances, remember next term we're going to prove that it's not a linear relationship between depth and length. And if we're assuming it is, when we get into extra long lengths, these sizing guidelines might not be good enough for us. If you're using a weird layout, something different than what you would see in a standard layout, that could have an implication on these sizing guidelines. If you have large transfers, so you have something big coming down a whole building and then it stops and has a transfer, that could make a change. We're going to show an example with a transfer that we're going to assume is a transfer. We're going to take that into account, but we're going to assume it's something relatively normal. We're not assuming that it's a transfer of a 30-story building at the second floor. That would be something unusual and probably wouldn't fall into these sizing guidelines. Maybe it's a story or two that we're talking about. If you're using the material in a unique way, if you're doing something outside of the norm for the material, this used to be a really good clause when we had just residential framing as our guideline for timber, for wood framing, for our sizing guidelines for wood. Anything in mass timber would have been using the material in a unique way. If you go into your downloads or helpful downloads module, you will find a file called sizing guidelines. In that, there is a separate page specifically for mass timber. So as we introduce each one, I'm going to remind you what each thing kind of looks like. We've already talked about these materials, so you have a good idea. I'll also usually provide you with what is kind of the normal range of products of that material. Sorry, I'm freezing. I'm just going to grab a blanket and put it on my lap here. All right. So the first one we're going to talk about is corrugated metal deck. Remember, our corrugated metal deck spans from joist to joist to joist, or purlin to purlin to purlin, or purlin to joist. But it is spanning a relatively short distance, and it is our surface. We'll put a finish on top of it, but it is the thing that fills in our, sorry, the blanket is all caught up on me now. It is what provides our enclosure, essentially. We will put our roofing or our floor, if it's metal deck, it's probably roofing. If it's just plain metal deck, it's probably roofing. Maybe if it's a house, they might do plywood on top of the metal deck and do the roofing that way. If it's a floor, I mean, they might put plywood on it and do a floor that way. But normally if it's a floor, it's concrete on metal deck. So the sizing guideline for corrugated metal deck, which is just metal deck, we often call it, the depth based on the sizing guideline is the length it's spanning divided by 50. Now this is talking about how far apart the supports are. A piece of metal deck can come in a very, very, very long strip. But what we're talking about is how far it spans. And it only spans a relatively short distance because we've got joists or purlins at some regular spacing picking up that metal deck. Typically, it's available in, you all right? Yeah. It's typically available in 38 millimeters or 76 millimeters deep. It is most common to use 38 millimeters. I often see when we get into the projects in second term for studio, students again and again and again picking 76 millimeter metal deck for no reason that I can or that I can figure out. I can't see the reason why. It has to be a really good reason why you'd go to 76 metal deck. It might be that you need your joists to be that much further apart. You can imagine that if it's double the depth, it can span double the length. But often people don't take advantage of that. They just say, well, 76 must be better, I must use it. But that's also way more expensive. Even using 76 metal deck with joists at double the spacing doesn't work out to be cheaper. Having gone through the calculations, 38 metal deck is going to be the cost that sets your system. The cheapest decking system is going to make for the cheapest system. It's funny, we don't talk about it much. We don't use calculations for it very much, but it is going to be what sets the cost of your system. It's going to have a trickle-down effect through the entire thing. So 38 metal deck is going to be where you start for a steel building with a roof, unless you have hollow core, but we'll talk about what that is in a few minutes. So if our joists are at 2 meters on center, our joists or a purlin are at 2 meters on center, what depth deck should we use? Well, we know our sizing guideline is L divided by 50, and if our length, which is how far our element is spanning, and our deck is spanning from joist to joist to joist, and they're 2 meters apart, the length our deck is spanning is 2 meters. So our depth will be 2 meters or 2,000 divided by 50. Well, that works out to 40 millimeters. Pretty darn close to 38 millimeters. I would always say don't round down, but I can tell you that 2 millimeters in this instance, we can use our 38 metal deck. So we would probably put 38 metal deck on our drawings for this. So the deck comes in 38 and 76, which I already said. The 38 is very close to 40 millimeters. We should use the 38 millimeter corrugated deck we would use that most of the time. This, of course, means that whatever supports deck would often be 2 meters apart at a maximum. So if you know that 38 metal deck is the cheapest system for your entire building, that means whatever supports it is going to want to be every 2 meters. So corrugate or concrete on corrugated metal deck. So you can see here we've kind of got punched holes a little bit in the side of this metal deck. That's grabbing a hold of our concrete and making it composite. Sometimes you'll hear it called composite metal deck. The sizing guideline is depth equals length divided by 20. Again, length here is how far the deck is spanning. It comes in, well, the most common assembly for our concrete on metal deck is 64 millimeters of concrete on 38 millimeters of metal deck. This is using normal density concrete. The only reason I'm saying that so explicitly is because when you look at the dead load list, it has ND written for the concrete, but that's saying normal density. Normal means it's the normal thing to do, and it is what's done the majority of the time. So 64 concrete on 38 metal deck, and this here does not mean that, well, I'll show you exactly what that means. I think I've drawn this for you before as well. What we're saying is that we have our deck is 38 millimeters deep, and then above that we have a total of extra 64 millimeters. But these flutes are also filled in with concrete. So this is where I've said, if you're looking at the dead load, well, no, I haven't said this yet. You will find this out. When we start talking about dead loads next week, don't start from basic principles and try to figure out the volume of the concrete. You will be given how much that weighs. So don't worry about that next week. You'll be given that information, but you don't need to go calculate the volume of concrete for this. So if our joists are at 2 meters center to center, what depth of concrete on metal deck should we use? Well, 2,000 divided by 20 equals 100 millimeters, which is pretty darn close to our 102 millimeters for our 64 concrete on 38 metal deck. So why would the concrete on metal deck span the same distance as the metal deck? The concrete on metal deck should be much stronger. Why would we span them the same distance? Well, this is where knowing what the application are is really important. The flooring usually has a higher cumulative load on it than the roof. The roof, with its lower load, can have the weaker material spanning the exact same distance as the higher load on the stronger material. So they would work out to be able to span the same distance. So again, if 102 millimeters is our most common assembly, 102 times 20, well, that gives us that about 2 meters is a pretty darn good system for our joists. 2 meters or less for concrete on metal deck or metal deck is where our joists or purlins need to be. That's just ubiquitous. 2 meters or less. That's where you're going to start. That's what you're going to draw again and again and again. So our open web steel joists. So these are the things that are picking up our metal deck or our concrete on metal deck. Now, we've already said that what's normal is for our deck to span 2 meters. Doesn't matter if it's concrete on metal deck or metal deck. It's spanning 2 meters. Our joists then need to be at every 2 meters or less. That is going to be the standard. There are definitely going to be instances where that is not the case. For sure it is. But we're talking about the normal boring stuff. And the normal boring stuff, they're going to be every 2 meters. They typically come in 2-inch increments. We're going to work in metric and say 50 millimeter increments. So if I ask you how deep an open web steel joist should be for a particular length, I don't want the exact calculation. I want the exact calculation rounded up to the next nearest 50 millimeters. So if your calculation is 380 millimeters, well, I want 400. If you went down to 350 millimeters, you're giving me something shallower than the minimum recommended depth. You wouldn't want to do that. You could in the final design make that call, but you wouldn't want to do that right now and then get a nasty surprise when the engineer comes in and does the final design and say, whoa, 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 you need a 400 millimeter deep open web steel joist. You haven't left yourself room for that. Now you're going to have deeper ceilings than what you've drawn. So the sizing guideline for open web steel joists is length divided by 16. So how deep would our open web steel joists need to be if they're spanning 9 meters? 9,000 divided by 16 equals 562.5 millimeters. Well, great. We have a depth now, but we know that that's kind of a weird increment to put on our drawings. So we bump that up to the next depth. We would say we should assume 600 millimeter open web steel joists on our project. The calculation, if it's lightly loaded, maybe we'd be able to do the calculation later and get that it's 550. Maybe we have really heavy industrial loads and we'd find out they need to be 700. But if we know that this is a relatively normal building with no weird surprises in it, a 600 millimeter open web steel joist is going to be a pretty good choice for our building. So if we're assuming this is picking up our 38 metal deck and our 64 concrete on metal 38 metal deck, how often do we need them to be? Well, we've already learned that that's about 2 meters on center because this sizing guideline is assuming that it's normal, and normal for these is about every 2 meters on center. So we would want for our drawings for a 9 meter long spanning open web steel joist, 600 millimeter deep open web steel joists at 2 meters on center. And that would be a great thing to put on your drawings. So before we go on to the rest of the steel sizing guidelines, let's just talk about what is available for normal steel sizes. We have square and rectangular HSS sections, circular HSS sections, angles, channels, and W sections. Yeah, I know our W sections look like eyes. Well, they used to be called I-beams, and there is a whole set of members called I-beams. When we started getting better at processing things and making machinery help us kind of develop these sections, the newfangled thing that came out in, I don't know, probably the 40s, they started rolling wide flanged members, which means they were a little bit wider at the top and a little bit flatter. And because they were the new thing, we called them W sections to differentiate from the I sections and the S sections. Well, now they're just the norm. So even though we call them W sections, they're shaped like an I. So here are normal sizes that are available in these sections. So a W section would be W and then something suggesting the depth. Now, the depths are not exact. These are not the exact final depth of these members. A W410 is not exactly 410 millimeters deep. But since our sizing guidelines are kind of approximate, it's a pretty good place to start with our drawings. Channels, same thing, approximate depth. If you look them up in the code, you will see that there's another number here. It would be W100 by 19, for example. That second number would be the weight per linear meter of the element. We're going to talk about that next term. Channels, same thing. The second number would be the weight. So you could tell at a glance, kind of comparatively, how much they weigh. And weight is our direct association with cost. HSSs, which are elements that we take flat steel and kind of fold them or roll them into the shape we want, not kind of heat it up to make the shape we want. They give us exact dimensions, but they don't tell us anything about the weight. So it's not as obvious to kind of tell at a glance what the relative cost is of these. So do you remember when we talked about tributary areas and tributary widths? I talked a lot about the difference between a river and a brook and a creek, and how if you came across them in the woods, they're all rivers. It's only when we're trying to categorize them that there is any meaning associated with these things. That applies for us right now. Steel beams are steel beams. Whether we're calling them a purlin or a beam or a girder is to just help us in our mind figure out what their hierarchy is. A purlin is a beam that is not doing that much work. It is usually just picking up concrete on metal deck or metal deck, and it is usually at 2 meters on center. So it's a relatively lightly working element. Our beams are usually the element that are picking up the purlins. So we wouldn't know the exact spacing of those because they'd be dependent on the length of our purlins. And then a girder is a beam that's doing an extra hard job. We don't always know what that extra hard job is. Maybe we know that there's really high loads in that zone. Maybe it's picking up a transfer, whether it's supporting another beam or a column above. I've had students in the past say, well, I sized it like a girder the way you said, but it was too deep of a beam for me, so I'm going to call it a beam. Well, the problem there is now you haven't left enough depth for your element. Calling it a purlin or a beam or a girder isn't going to change the final math in the design. And if you called what you can clearly recognize should be a girder a beam and size it accordingly, you're going to end up with a beam that's not this deep, but this deep in your preliminary sizing. And then when you do your final design, you're going to find out that you do in fact need a beam this deep. And if you're telling your client you only need this much room, it's going to be a nasty surprise that you need more depth. So always be conservative here. If you see a beam doing something weird, call it a girder. It's only going to give you a nice safe buffer in the end. So our beams, and remember a beam is a purlin, a beam, or a girder, come in standard sizes listed in the CISC Steel Handbook. That list is the list that I showed you on the previous page. The W sections, the channels, and the HSSs would be the most common. There is a sizing guideline in the sizing guideline chart that tells you that a width with a sizing guideline of 1/2 to 1/3 of the depth could be used. I hate the width sizing guidelines because they're absolute crap. The width varies greatly even within depths of a particular type of beam, to the point that I'm not going to ask you a width for any of these things for our steel beams, just because they have almost no relationship the way some of the other beams might possibly have a relationship. You don't need to worry about the width for the steel beam, but it might come in handy if you're not picking a real beam and you just want to draw something, drawing it to 1/2 to 1/3 of the depth for the width. You'd probably have a pretty good drawing, but it would give you no kind of real information. How deep do purlins, beams, and girders need to be if they span 8.5 meters? Remember, a purlin means that it's something that we've got every 2 meters. A beam is probably something that's picking up the purlins, and a girder is probably something that's working extra hard. We don't have the context of what they're talking here. This is just to help us compare the depths for the same span. So a purlin, our sizing guideline is L divided by 25. So 8,500 divided by 25 is 360. If we go back to that list, we have a C380, or we could have a W360. So those would be good choices for our purlin, assuming it was a thing that was every 2 meters picking up the deck. If the member was something supporting purlins, maybe we'd want to use the beam sizing guideline. It's length divided by 20, or 8,500 divided by 20, giving us 425 millimeters. So we'd want to go back to that sizing list, and we'd see that the next size up would be a W460. That would probably be a good depth to put on our drawings. Now remember, For C sections and W sections, that depth is not exact. It is not exactly 460 millimeters deep. You could look it up if you wanted to go find the steel book and look up what it is. But for what we're talking about right now and for a set of preliminary drawings, saying something that's 460 millimeters deep would be pretty good. A girder. If we looked at the set of drawings that showed the beam that was 8.5 meters long and there was a transfer column sitting on top of it, we'd say, whoa, that's a beam that's doing some extra hard work. Maybe we want to make sure we give ourselves enough depth for that bad boy because it's going to be working really hard, and let's size it as a girder at this preliminary stage. If we find out later that it can be shallower than that, great, we'll be able to have a bit more headroom, but we don't want to find out later that we were wrong and put something way too shallow. So we'd use our sizing guideline of L divided by 15, which gives us 567 millimeters. So we'd probably go back to those sizing guide or that list of member sizes that I showed you, and we'd see that a W610 would be the next beam. You can see that if we had sized it as a beam and it was supporting extra weird loads, we might have undersized it. We might have left, almost 200 or 150 millimeters or 6 inches too little in our ceiling space to fit our beam in. So the purlins should be, if it's a purlin that's 9 meters long, it would be a W360 or a C380 at 2 meters on center. So trusses. Trusses are often, we don't use trusses lightly because they're expensive. They have the advantage that they take out a bunch of material and they let us or it lets us use elements, create members when we don't have available depths. So if we find something needs to be deeper than what we have available, we might go to a truss. Now a truss is going to end up being deeper than the equivalent beam. The beam would probably be a girder. So we'd probably be comparing these trusses to a girder. And if we looked at our girder sizing guidelines, it was L divided by 15. Our truss is going to be L divided by 12. So that means if they're both doing in the exact same spot, if we switch from a girder to a truss, it's going to be deeper, but it's deeper with all of these voids in it. So these would be custom made by the fabricator. Often the base building engineer might get involved in the design of these, at least for a preliminary design. The fabricator would be designing the connections. These ones, you could very explicitly go to a custom depth. Like if we got that the calculation needed to be 935 millimeters deep, we could make it 935 millimeters deep. If we had no real constraints though, we'd probably still kind of keep it to 50 millimeter increments. So how deep would a truss need to be if it spans 8.5 meters? So we'd take 8,000 divided by 12 and we get 666 millimeters deep. I'd probably recommend a 700 millimeter deep truss. If this was a very kind of refined design, very high end, very high profile, we might later on in the project look at refining it to something very specific. But at this point, I would probably round up to the nearest 2-inch increment or 50 millimeter increment. Let's talk about our columns. The sizing guidelines for columns is H divided by 40 to H divided by 20. We're going to stick to the H divided by 20 kind of rule here because we're going to be talking mostly about short columns. The standard sizes, it's the same sizes that we would be talking about for we'd be looking at W sections, HSSs for this. We wouldn't use angles or channels for columns. So we'd be sticking to our round HSS, rectangular or square HSS, or our W section. So we'd go back to that same list that I showed you to pick from. So what size do the columns need to be if they're 3 meters tall? Well, this is a short column, and I've told you to stick to the h divided by 20 range of these. So it would be 3,000 divided by 20, or 150 millimeters. So if I was going to pick something for this, I would say a W150 or an HSS 152 by 152, or a round HSS that's 152 millimeters in diameter. Let's take a look at this simple diagram where we have 1, 2, 3 different column types. This member here is supporting a column above. Both of these bays are 12 meters long, so I guess this member here, because it's supporting a column above, is 24 meters long. Our bay size here is 8 meters. It looks like we've got a deck of some sort spanning the full length, but it's being picked up every so often by what looks like joists in this zone and beams in this zone. Seems weird that they'd switch from joists to beams. We don't know what the context there was, but we'll assume they had a really good reason for it. So we want to size the concrete on metal deck. So they've told us that this second floor is a floor, in fact. So the 2, that's just context, that usually that's the context for a second floor beam, second floor deck. So our deck, we need to size our deck, our joists, our purlins, our beams, and our girders. So we have 2J01, 2B01. Interesting. They've labeled this a beam. All of these are the same beam. But we know this looks to be something that's some regular spacing, and it's supporting our concrete on metal deck. I think when it comes time to size 2B01, I'm going to call that one a purlin. 2B02 looks like all it's doing is supporting half of these joists in the purlins. So it seems fair to call that one a beam. Well, this 2B03 is really long. 24 meters is a pretty long span. And look at this, it's supporting a column above. So not only is it like kind of getting into a large span length, we've got a transfer happening on it. That makes me think maybe I'd want to think hard about designating that as a girder or a truss. So deck 2D01, it's concrete on metal deck, which they've told us here. How far is it spanning? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 bays or 13 spaces in our 24 meters. So our total length is 24, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's fix that. 24 divided by 13. Let's fix that right now. I'm going to fix that while I'm talking to you guys, if my computer wants to behave. All right, let's take a look at this right now. This should be 13. 24, 1846 millimeters. 1846. One 846 divided by 20. All right. Just wanted to fix that right now while I had it here. So we saw that it was the full length of that was 24 meters, but there was a support every some distance, and there was 13 of those. So 24 divided by 13 gives us 1846. So that's how far our deck is spanning. It has a support every 18 or 1.846 meters. To figure out what depth we need, we have 1846 divided by 20. So the sizing guideline for concrete on metal deck is L divided by 20. We do that math and we get that we need something that is 92.3 millimeters deep. Well, 38 deck supporting 64 concrete, we know is industry standard. It looks like maybe we could have spaced our joists a little bit more. Maybe we know something about this system, that there's heavier loads. I don't know. Maybe this worked really well for the layout. But it works within our range, and it's pretty close. 102 is the total depth of our 38 deck 64 concrete. So it seems like a really good choice. Joist 2J01 was spanning 8 meters. So we have something that is 8 meters long. It is about 2 meters on center. It's actually 1.846 meters on center, but we know that's pretty close to our 2 meters on center. So it seems like our sizing guideline is still a good choice. It's not doing something weird. So we take our 8 meters and divide it by 16, giving us 500 millimeters. So it seems like a really good choice would be a 500 millimeter deep open web steel joist. Someone in Dave's office just tested positive. Okay, so 500 millimeter open web steel joist seems like a really good choice there. Let's talk about purlin 2B01. It was at the exact same spacing as our joists. Remember, joists and purlins can be interchanged. They have different sizing guidelines, so you need to pay attention. A purlin is still a beam, so calling it 2B01 is totally normal, but we, looking at the plan, can recognize that it is doing the job of a purlin, so we can be a little bit loose on our sizing guideline. We can go with the sizing guideline that's a little bit a lighter criteria, the purlin one. It's only picking up deck, and it appears to be about every 2 meters. So our 8 meters divided by 25 is going to give us 320. I actually don't like this one. We're going to change this. 2B01, I'm going to change this to a C that works and a W that works. I had a different number here previously, so I'm going to fix this little typo right here, right now. Let's just go back and take a look at what we had here. We could have a C380 or we could have a W360. So I'm going to update that right now while I have the opportunity. So a good choice for our purlin would be a C380 or a W360. Again, at 2 meters on center. So both of those would be at 2 meters on center. So for the same span, the purlins and the open are shallower than the open web steel joists, but they probably end up being a heavier system. So there's a payoff there. If you want the shallower system, go with the purlin, but understand that it might be a little more expensive. Joists become cheap when you have a lot of them and they're repetitive. If you only have 3 or 4, the purlin is definitely the way to go. So beam 2B01. So that was our beam that spanned 12 meters and was picking up our purlins. So that was the one spanning from CO1 to CO2 and CO2 to CO1. Our beam sizing guideline seems to be like the appropriate choice because it is supporting purlins, which we've said is typically what a beam would do. If we use the purlin sizing guideline, we'd get a shallower beam as our answer, and then we could get a nasty surprise when we go and do our final design to find out we should have guessed that there was a deeper member. So our length is 12 meters. Sorry, yeah, I said that 12 meters, right? Yeah, 12 meters. Our sizing guideline is L divided by 20, or 12,000 divided by 20 gives us 600. So we should use something that's greater than 600 millimeters deep. If we go back and look at that list, a W610 seems like a really good choice. If we had used the purlin sizing guideline, we would have gotten something shallower, and we would have been unpleasantly surprised in the design. Now, 2B03 we talked about already and said that it seems to be spanning a really far distance. Let's go ahead and call that one a girder. It's also got a transfer coming down on it. So something that seems to be doing an extra big job, we'll use the girder sizing guideline. Its full length was 24 meters or 2,400 millimeters. Our sizing guideline is 15, and we get that it needs to be 1,600. Well, there wasn't anything available in the 1,600 range. We can make custom beams, and we'll talk about that next term. They're called wide welded flanges, but that doesn't seem like maybe the place we want to go, or we don't know much about that, but we do know that trusses are an option. Let's take a look if 2B03 was a truss. So our length is still 24 meters, but our sizing guideline is L divided by 12 now, and we would get that we could do a custom 2-meter deep truss in that position. So this is where knowing what your floor-to-floor height is, that becomes really important. If our floor-to-floor height is not very high, that either wants to be at a perimeter wall or embedded in a partition wall, because that's going to be 2 meters deep. If our floor-to-floor height is only 3 meters, we've only got a meter of clearance, and there's not many people, maybe my kids, could fit under a meter clearance. So let's take a look at our column, CO1. Well, they did tell us that our floor-to-floor height was 3.2 meters. So that only leaves 1.2 meters for that truss that we designed. But maybe that's the outside edge of the building. We don't know what the context was. In fact, they drew it with a dotted line around it. So that could have been the outside perimeter of the building. Our sizing guideline is H divided by 20. When we calculate the 3.2 meters divided by 20, we get 160 millimeters. We want to make sure we give ourselves a nice little buffer here, so we might bump that up and say that we should use an HSS 203 by 203. Column CO2. Exact same. Well, if we looked at those, CO1 and CO2 weren't doing the same job. CO2 looked like it was picking up twice the tributary area as CO1. So this is where it's really apparent that our sizing guidelines, while excellent and helping us out, actually aren't perfect. We can see that this tells us these need to be the exact same thing. But when we do the final design, we can see that one of them is going to actually need twice as much capacity as the other. We're not really sure how that comes into play. Is that just about making it bigger? Could we fill it solid? We're going to talk about all of those things next term. All right, let's move on to lumber. We're going to be talking about dimensional nominal lumber right now. I will touch on some of the engineered products as well. So dimensional nominal lumber, sometimes nominal, sometimes dimensional, is what you go into Home Depot and purchase. That was originally cut as full-size lumber, so our 2x6 is not actually 2 inches by 6 inches. It's 1.5 inches by 5.5 inches. Originally it was 2x6, and it was very rough sawn, and then it goes through a planer where they smooth it down and give it those customary kind of rounded edges, and that takes off 1/4 of an inch off the top and bottom and 1/4 of an inch off the side. It takes 1/4 of an inch off the side of a 2x6 and a 2x4. As we get into a 2x8, 2x10, and 2x12, we're actually taking off cumulative 3/4 of an inch, so half of that each side of the member. These are typically used for joists and studs, so these are not open web steel joists, these are wood joists. Beams, built-up beams, where we screw multiple plies together. We would always use at least 2 plies if we're talking about a beam and not a joist. Posts, we would use at least a 4x4, or we can do built-up posts where we screw plies together. Again, we would always screw at least 2x4, 2 2x4s or 2 2x6s together. Plywood. Plywood is something that comes in 4x8 sheets. Those are 4 feet by 8 feet sheets. You can get them bigger. They're a pain in the butt to move around. I know when I try to load, if I have to go buy plywood, I can't do it on a windy day because I do not have the strength to move it around in the Home Depot parking lot in a full-on gust of wind. It comes in a range of thicknesses, but the ones we're going to be talking about structurally would be 1/2 inch and 3/4 of an inch. We might structurally use 5/8, 7/8, or 1 inch, but that would be when our normal things don't work. And what we're talking about today is normal things. I-joists. I-joists are a proprietary system. They're designed by the fabricator, and they really are just a bunch of wood shavings glued together in chunks of wood, top and bottom, where they're glued together. The depth would be sized using preliminary sizing. Sometimes maybe we'd use a design aid to figure out what depth they would need to be to go on the drawing. But the final number that gets signed and stamped with an engineering stamp would be by the supplier. These we would put in instead of our wood joists. Now, we wouldn't start with these. This isn't typically where we'd start. The cheapest thing in wood is going to be using nominal lumber, or a 2x4, 2x6, 2x8, 2x10. Even going to a deeper system, it's often cheaper to stick to the lumber. We would go to an I-joist if we can't get the spans that we want, because regular wood is limited by length, where these can be made to be longer, or where we're limited in headspace or headroom, and we really need to go with a shallower system for the same span and loads. We can, when we're limited by wood beams, so that's when we would take 2x4s, 2x6s, 2x8s, 2x10s, 2x12s, and screw them together, we can go to engineered wood that is kind of more used for residential construction. You can use it in bigger projects, but this tends to be used to enhance regular lumber construction. So PSL is parallel strand lumber, where I find it looks like a bunch of apple peels that are all laid out more or less, pretty much in the same direction and kind of injected with glue. They come in widths of 68, 89, 133, or 178, and they have available depths of 241, 302, 356, 406, and 457. You can cut them to narrower widths if you need to. Sorry. This is my third 3-hour lecture that I filmed today. So my throat is getting sore and I am getting very tired. I am on hour 7 of recording. Okay. So they can come in lengths up to 20 meters. You could get longer, but 20 meters is about the length of a big truck, like the big ones, and it's harder to even get a permit to move the lumber around then. Very similar with laminated veneer lumber. Laminated veneer lumber, instead of apple peelings going around, it's more like unpeeling the log and like rolling it out into a big flat sheet as you peel it. And then you cut it in strips and glue them together. So it looks slightly more organized. They have some slightly different properties. Their widths are slightly different, and most of the depths are the same, but this comes in a few deeper ones. They're almost interchangeable. One is slightly stiffer than the other, and one is slightly stronger than the other. I have found that if on a project I use or specify PSL, the contractor will call up and say, "You're crazy, you can't get PSL, all anyone uses is LVL. Why would you do this to us? Please put LVL on the project." So I have to do a check because they're not just perfectly interchangeable, and I'll put LVL on. So next project comes along and I'm like, I'm not going to make that mistake again. I'm going to use LVL. And this contractor will call up and say, you're absolutely crazy. No one works with LVL. All anyone does is work with PSL. Why would you put it on the drawings? So it really has to do with comfort level, how they source it, where they source it. Even geographical locations can make a slight difference in it. But knowing who the contractor is can really help that process. I would say it doesn't really matter, except that there are slight differences in their properties. Mass timber. So mass timber, we're getting into the big elements here. So mass timber is when we take our 2x4s, 2x6s, 2x8s, and stack them on top of each other and glue them together. And that would be our glue lamp, for example. So we're making a big rectangular beam by gluing a series of smaller elements together. This isn't something we use just to toss into a drawing instead of regular lumber. This would be a very thoughtful thing we would do. Either it's a showpiece, or it's because the demands on it are real, and we're probably doing mass timber as a design aesthetic or a design choice for a larger building. CLT, this is when we're gluing elements of lumber in together to make panels. We often make 5 to 7, we can make 3, 5, 7 thick panels deep. This would replace our joist and plywood deck system or our stud and plywood shear walls. They come 2 feet to 10 feet in width, and they can come up to 60 feet long. That does not mean that we can make it span 60 feet. It would need intermediate supports in there, but you can build it to be a 60-foot long piece. So the sizing guidelines for plywood, I don't care. I don't care what the sizing guidelines are. It's typically 16 inches center to center for joist spacing. So our plywood can span 16 inches. Our roof and walls are relatively lightly loaded, so our 1/2 inch plywood can span 16 inches. And for floors where we've got higher loads, our 3/4 inch is going to span our 16 inches. That means our joists and our studs are going to be 16 inches on center. In specific loading conditions, we can do 12 inches or 20 inches. I've even seen 8 and 24 inches, but those are thoroughly designed. That is not something we toss on the drawings at a preliminary design stage without very thoughtful consideration. Tongue and groove deck is something we might do to replace metal deck if we were in a bigger style system. So this means that it would be something spanning from purlin to purlin or open web steel joist to open web steel joists, not our wood joists anymore. This would be being used in our kind of bigger systems. You often see them in pool areas because the metal deck has a tendency to rust. And the wood holds up really well. Even though it's a wet environment and that can impact the strength of wood, it holds up better in that moist environment than the steel deck does. The 38 millimeters seems like a funny number to make our metal deck when we could have made it whatever we wanted. The wood, our tongue and groove, was the normal thing in the industry. When metal deck came along, it was to say, we can replace your tongue and groove. So it wasn't that tongue and groove is replacing metal deck. Our metal deck started replacing our tongue and groove because it was able to span just a little bit farther. Look at our sizing guideline. It's L divided by 40. So if our metal deck could span about 2 meters, our tongue and groove can span just a little bit less than that. So if we had an example where it was 1.6 meters span, or we had joists or purlins every 1.6 meters, our sizing guidelines would tell us that our tongue and groove deck would need to be about 40 millimeters thick. Well, that works out perfect because what we have is the most common is 38 millimeters deep. That also tells us that if we're using tongue and groove deck, our support system needs to be about every 1.6 meters. Remember, if it was metal deck for the same depth, we could span up to 2 meters. So wood joists. So these are these elements here that would be every 16 inches on center. Standard wood sizes are 38 or 89 millimeters wide, but 38 is normal. 4 inches, which is 3.5 really. 140, which is our 2x6. 184, which is our 2x8, 2x10, 2x12 deep. Remember, those are then shaved down to match these dimensions. If these are supporting plywood, how often should they occur? We know that they should be every 16 inches on center because our plywood spans about 16 inches. And we're talking about normal stuff here. We're not talking about fancy outside the box stuff. Our plywood spans about 16 inches, therefore we need a joist roughly every 16 inches. So how deep should our joists be if they're spanning 3 meters? We can assume that they're also happening every 16 inches. So 3 meters divided by 16, which is our joist sizing guideline, is going to give us 188. I don't like sizing down, and I thought I went through and kind of finagled all of these things. But you know what? I'm going to give us 4 millimeters. 4 millimeters is almost within kind of tolerance errors and things like that. And these are our preliminary sizing guidelines. But I'm only just making this decision. I'm running a risky game here. If I went through and finally designed this and found that a 2x8 wasn't going to work and I needed 2x10s, that's a big difference on the project. So I want to be really smart about making this choice. I'm going to say that maybe I know something about this project and it's, on the lighter side of normal, and I'm going to go with the 2x8s. So again, if they're supporting plywood, how often should they occur? And we know that the plywood can span 16 inches, so we should have these every 16 inches. So 2x6s at 16 inches on center, or a 38 by 184 at 400 millimeters center to center. Oh, really sorry, guys. Engineered eye joists. Let's take a look at those. I've listed kind of what some of the sizes could be there. There's actually a mistake in that. That's slide 34. One of these has a typo, I believe, in the kind of available size there. So these ones, they're not the first choice we'd go with. We'd put them where we just need things to span maybe a little bit farther. So how deep should eye joists be if they're spanning 7 meters? Remember, our 2x8s spanned about 3 meters, and that was pushing it. So we have 7 meters. Our sizing guideline is 18. So 7,000 divided by 18 gives us 389. Well, we didn't even have 2x material that was that deep by any means. So this seems closest to the 406 millimeters eye joists, so the ones that are 406 millimeters deep. So we would want 406 millimeter deep engineered eye joists. And we know they must be how far apart? 16 inches on center, because that's normal. Maybe final design, we'd find out something else, but normal is 16 inches on center. So the question here says, what if they're supporting 38 tongue and groove? How often would we need them? Well, we know that this means we probably need them at 1.6 meters on center. So that would be fine for the tongue and groove. But what does it tell us? It seems like this might be a little bit funny. Maybe we wouldn't have wanted to go with this depth because we know this should be telling us they're every 16 inches. I'm not comfortable with this one. I think I'd go back and change the math on this one. In fact, I think I'm going to after this year's lecture. I've talked it through with you guys, but I think I'd go through and change that next time. So you can see here that I actually did write 406 engineered joists at 16 inches on center. So I recognized this issue at one point, but didn't change the question here. So I'm going to change that because I don't like that. We're going to assume that this is supporting plywood, which would be the more normal situation here. Plywood, this is slide 35. I'm going to change that to 3/4 inch plywood. So when you see this, you're going to see this saying 3/4 inch plywood instead. Wood beams. Now, our cheapest is always going to be starting with regular lumber. So that would be something with a built-up section with our 2x material. We wouldn't go less than 1 ply. A ply is one ply is 1 2x whatever. 2 plies, we've screwed 2 of them together. A 3 ply, we've screwed 3 of them together. Lumber beams have a sizing guideline of L divided by 14. They'd be something picking up our joists or our I-joists. Engineered beams would be our PSL or LVL. They have a slightly better sizing guideline of L divided by 16. Unless we know they're working, if that beam is working extra hard, we might switch to calling it a girder just because we know it's doing something kind of extra difficult. Beam width. Beam width is a pain in the butt. I hate talking about it, but it's helpful because it helps us guess what to draw. The width can vary between D divided by 2 to D divided by 3. You're going to see that if you draw it, you're going to have a pretty good idea of what you expect it to be. For a beam, it's probably not going to be square. Again, you intuitively know this. We're going to do the math next term about why that's the case. But a beam doesn't often end up being square. And do you use the number you calculated? Do you use the number you rounded up to? Do you use the metric number or the imperial number? So if we calculated we needed something 180 millimeters deep, do we use the 180 or the 184 millimeters because we know it's a 2x8, but we're talking about it in metric? Or do we use the 203, which is the 2x8, talking about it in imperial, where we actually would use 203 possibly for the calculation? The answer is, I don't know, kind of varies. I can tell you that if I gave you a calculation, possibly say on the assignment, that there would only be one of all of those variables that would be an option in the multiple choice. So there might be other options in the multiple choice, but they wouldn't be ones that you could calculate as possibly being right. I would make that at least the case for you. It's not to say that there couldn't be other options, but only one of them will be in the given list of options that you can select from. None of the other options would be something that worked. So our lumber beams are from 2 to 4 plies of standard lumber sizes. The columns can be built up or solid standard sizes. Engineered beams and girders are glued and laminated products. So our LVL, PSL, and maybe our glue lam. So assuming the datum is 2.438 millimeters, size the plywood deck, the 2J01, the 2J02, the 2B01 to 2B03 beams, and the columns C1 to C04. And then they've noted, pay attention to the column above 2B03. So it looks like 2B03 is doing something kind of funky here, that we're going to want to make sure that we pay attention to that. It looks like 2B02 and 2B03 each span 8 meters. Our joists span 4, and 2B01 looks like it repeats itself a few times, and it spans 4 meters. We've got CO1 at the two ends. All three of these are CO2. CO3 here, there's a bit of a flaw in that image. So CO3, I'm going to change that to CO5, CO4, and delete column above. So you guys are going to see a slightly edited version of this where we're actually looking for CO1 to CO5. I actually did edit that, but somehow it's not showing up in this image. Oh, and I took the animations are doing funny things. Let's just take those out then, because that's a pain. Slideshow from current slide. Make it so I can see it with you guys. Okay, so let's start with the deck. We know that deck can span 16 inches. We can actually look at this, and they've told us that these are at 16 inches on center. We can use our sizing guideline, and it would give us 10 millimeters for decks, but we know that floors are typically 3/4 of an inch, 19 millimeters plywood. So this is greater than we needed, but 3/4 of an inch we know is industry standard for our floor. So let's not mess with the industry standard unless we need to. So 2J01, we can see that it spans 4 meters. Our sizing guideline for joists is 16 millimeters. So we have 4 meters divided by 16, we'd get 250 millimeters. We'd want to bump that up a little bit. We never want to go down. The next size that works is going to be our 2x12. So we would have 2x12 joists. 2J02, we want to size as an I joist. So it's spanning the same distance. We've got 4 meters divided by 18 gives us 220 millimeters. We want to pick what I joist works, and from the list of I joists, 240 was an option. So we can use a 240 I joists. Seems like there's I'm gonna clean up some of this. Because that I joist is working pretty well. There's a little bit of a buffer in it, but no more than the 2x12. But you know, there's only 46 millimeters of difference between the 2x12 and the 240 I joist. That's not a big difference. And there's an added cost in this. Maybe headroom is a really big issue, and we'd want to think about that. So we'd want to really think, is it worth using the I joist? Is it worth making that switch? My guess is that the 2x12s are probably a great choice, but maybe looking at the drawings, we know that there was something going on there. Maybe that in that region we needed more headroom. There's probably a good reason there. I hate these animations. Okay, so let's just put everything out on the table here. So 2B01. First place we want to start is regular lumber because that's the cheapest. We saw that 2B01 spanned 4 meters. We get 4 meters divided by 14, which is a regular lumber beam, gives us 286. Well, 286, that's the size for the 12-inch deep members, which is really 11 3/4 millimeters deep. Well, if we look at the width guidelines, it's somewhere between 2 to 3, or a half to a third of the depth, which is 143 to 95 millimeters wide. Again, these are very loose guidelines for this. 2x12 members are 38 by 286. 3 plies would be 114 by 286. Seems reasonable because we don't know where in the half to a third rule we're kind of falling into. If we knew that this was heavily loaded, maybe we'd bump that up to 4 plies, but 3 plies seems reasonable. Do you use the 12-inch or the 286 to calculate that? Kind of depends on the mood. But looking at this, I think I'd use 3 2x12s to span that distance. So each one of those 2B01s would be 3 2x12s screwed together, kind of looking just like that image there. They told us also to size 2B02, which spans 3.33 meters. Just want to go back and check that my drawings have not. This is not the right drawing here, guys. I thought something seemed funny with this drawing. It did not update properly. So you guys are going to see a different plan here than what I'm talking about right now. The image did not get included in the file that I am looking at. It looks like it shut down before it's saved. There's some adjustment here where this is actually 5.33 meters. So you guys are going to see that, and the calculations are going to be kind of aligned with that. Our length will be 5.33 millimeters divided by 14 gives us 380. There's no regular lumber that deep, so it seems like we're out of luck. We can't use the cheap, easy option. Let's go and look and see if there's an LVL or a PSL that could work for us. We would say, all right, it's the same span, but now we get to use L divided by 16. We get 333 millimeters deep. So both PSL and LVL come in a 356 millimeter deep member. So again, for W, for the width, do we use the 333 or the 356? Do you divide by 2 or do you divide by 3? Again, some of that depends on context. This sizing guideline for width is crap. It's more about drawing something that looks reasonable. I'm going to use the 256 and I'm going to divide by 3. I get 119. Well, that tells me I should use 3 45 by 356 LVLs or 2 68 by 356 PSLs. That would be a pretty good assumption in a preliminary design. Our girder, which is the one with the column above, so this is our 2B03, spans 10.67 meters, and it's got a column at the midpoint of it above, or somewhere along it above. We just know that that's not going to have anything in regular lumber. If our 5-meter one didn't work, there's no way we're going to get a regular lumber to work. Well, we've got 10.67 divided by 12 gives us 889 millimeters. There was no PSL or LVL even available in those member sizes. We'd be reluctant to do it, but maybe this project has the appetite for it, that we'd want to look at a custom engineered wood glulam beam. So maybe something that is, again, this is all kinds of weird stuff happening in this. Glulam beam, that's a weird size for a glulam beam. That's going to show a better size for you guys there because our depth was 889. I haven't even given you all of the range of glulam sizes. I don't want you to have to get into that. That seems a bit kind of over the top. I'm just going to make the note here that a glulam beam would probably be a really good choice. So column C1 to column C4, our height is 2.44 meters. The sizing guideline is height divided by 30. That would calculate 82 millimeters. They did tell us that we'd need at least 2 plies for a stud or a post, or we'd want to use a solid 4x4. So a 4x4 is 89 by 89. Or we could have a 76 by 89. So we're not even going to look at kind of any other options. I'd probably even say that that needed to be, so C01 to C04. I'm going to say that that should be 3 38 by 89s, simply because this needs to be our minimum dimension. So if it is 3 38 by 89s, which is what you guys are going to see on your slide, 3 by 38 is going to give us 114. So we have all the sides greater than 82 millimeters because this is a column, it's not a beam. I'm going to pause it right here and I'm going to thread these videos together for you guys. I want to go fix all of those things right now. Okay, let's keep going with our concrete sizing guidelines. We're going to start with one that actually doesn't get used in concrete buildings, but it's a concrete material. We often use it with steel buildings or with masonry buildings. And this is hollow core slabs. They're concrete planks that have extruded holes in them, and we talked about that earlier in the course. And they come in 200, 250, 300, and 350 depths. 200 and 250 are the most common. You would often use the other sizes if you had, actually you can even get them in 150 as well. So I'm going to add precast 150 to list. Hollow core. You would only use those kind of weird, those less normal sizes when you were already using hollow core for the whole project and you needed those ones explicitly in certain regions. You probably wouldn't do a whole project with 150 hollow core. It just wouldn't be that economical. But if everywhere was 250, but you had a couple spots with headroom that needed 150 for one single bay, that's where it might become really economical to make that switch. Sizing guideline is L divided by 40. And remember, these are eliminating our metal deck and joist or purlin system. So either concrete on metal deck or metal deck. Also eliminating our joists or purlin system. So instead of metal deck spanning on joists, we just have our hollow core spanning. So if we had beams that are 8 meters center to center, what depth of precast should we use? So we have some grid spacing that has major beams every 8 meters. For the most part in the building, what would be a good precast depth to use? Well, our sizing guideline is 40 millimeters, so we take our 8 meters divided by 40, and that's going to give us 200 millimeters as an appropriate precast depth. So like I said, it comes in 150, 200, 250, and 300. Sometimes you will see those listed in imperial. If so, you could use that, but we're going to stick with the metric here. It really depends on what supplier it is. Sometimes one supplier will have two different pamphlets. They're often actually made at the imperial depth, even though their pamphlets say that they are the metric depth. So we had a project once where the architect was very upset about the extra 4 millimeters once they actually got to the project. I think the 4 millimeters are probably well within the tolerance of construction of a building, but I just want to be clear that they're often made at the imperial. I don't want to say always, because sometimes they're not. Some fabricators do it differently. So what's an optimal span for each of the depths, assuming we're talking about kind of the normal ranges of ones? Well, a 150 can span 6 meters, a 200 can span 8 meters, 250 spans 10 meters, and a 300, well, that could span all the way up to 12 meters for us. And those are really kind of the norms that we would go. One-way slab. A one-way slab is a cast concrete slab. So we put formwork on the bottom, we put rebar in, we pour in our liquid concrete, we let it cure, and then we take our plywood away. One way is when it's spanning from beam to beam. Very similar to our hollow core. So it's doing the same thing as our hollow core, but the difference is it's cast integrally into our beams. So our one-way slab and our beams usually kind of get mixed in together a little bit here. The sizing guidelines for a one-way slab is L divided by 40. Again, we would often cast these in increments of 50 millimeters. So if I ask you for something in the assignment, I am looking for 50 millimeter increments. So how deep does a one-way slab need to be if we're spanning 4 meters? 4 meters divided by 18 is 222 millimeters. So a 250 cast in place concrete slab is a really good option. 200, 250, and 300 slabs are normal one-way slab depths in Ontario. How far would they span? For a one-way, slab depths are often 200, 250, and 300 in Ontario, or what we normally cast. So how far can they span when they're a one-way system? Well, our 8-inch or our 200 slab is going to span 3.6 meters. Our 250 slab is going to be able to span 4.5 meters, and our 300 slab is going to span about 5.4 meters. Remember, our hollow core was able to span quite a bit further than that. Two-way slab. A two-way slab is when our slab can share its load out at each of the corners or at each of its sides. So I'm going to draw a little diagram here. I'm going to draw 2 of them for you. And I'll show you why, if a two-way slab is so much better, why we can't just use two-way slabs all the time. So if this is the diagram, this is a two-way slab. What we're saying is that everything in this triangle is going to that beam. Everything in this triangle is going to that beam. Everything in that triangle is going to that beam. If we stretch out the proportions of that, this tributary is going to this beam, this tributary is going to this beam, these beams over here aren't doing that much. This, just by default of where the load goes, is actually a one-way system. So it's not that we're just picking, we're not just saying, I want to make it a two-way system. You have to pay attention to what the dimensions are. If you don't have the dimensions of a one-way system, you don't get to use a one-way system. So you can tend to use a two-way system if your proportions for your sides of your floor are less than 2 to 1. So as you start to stretch that out, so you could have the long dimension be twice what the kind of side dimension is, and you'd still get the benefit of a two-way slab. Your smallest depth would be 150 to 200, but it's probably going to be the norm to be 200, 250, and 300 are going to be your normal two-way slab systems. So our sizing guideline for two-way slabs is 30 millimeters. So how far can we span if we're 8 meters? 8,000 divided by 30 is 266. So for that particular two-way slab, a 300 cast-in-place concrete slab would be a really good choice. If 200, 250, and 300 slabs are the typical slab depths that we tend to make, how far can each one span as a two-way slab? Well, we can have 6 meters for a 200 millimeter slab, 7.5 meters for a 250 slab, and 9 meters for a 300 millimeter slab. Concrete beams. So concrete beams have a neat kind of aspect that they can be cast as part of the slab. So what does that mean? If we have, and I think maybe I drew this for you guys last week. Maybe I didn't. I know I drew it recently. If this depth here is our slab, our beam that we get to use gets to be this whole depth. We can actually use and include the depth of the slab when we're talking about our beam depth. So concrete beams are L divided by 16. A girder, which is a beam that just looks like it's doing a bit more work, would be L divided by 12. Again, beam width, totally loose guideline. I'm not going to expect you to do anything crazy with that. If I made you calculate, I'd only give you one option that worked within that range. The cool part is it can be part of the slab. So pay attention. Am I talking about how deep can it be below the slab, or how deep is its total depth? So concrete beams, girders, and the width. What depth below the slab do we need for a beam spanning 9 meters if the slab is 200 millimeters? Well, we have 9 meters divided by 16, so 562.5 is the calculation. We're going to round up in 50 millimeter increments, so we're going to go to a 600 millimeter deep beam. We had a 200 millimeter slab, so that means the projection below our slab, because that full depth is our 600, we're left with a 400 millimeter projection below the slab. And if somewhere between a half and a third is going to be a good width, I've drawn this at 200 millimeters wide. Concrete walls and columns. A concrete column, h divided by 20. Concrete walls, h divided by 25. Again, they're custom made on site, typically in 50 millimeter increments. Not required, but that's what we're going to assume, especially in a preliminary stage here. Walls would never be less than 200 millimeters unless it was a short, lightly loaded, basically something very fancy and high end. But we'd be talking about 200 millimeter walls as a minimum for these things. So what would the size of columns and walls be for a building with a 4.2 story to story height? Our height is 4.2. Our rule of thumb changes from 20 to 25, depending on whether it's a column or a wall. So our columns could be 4.2 divided by 20, or 210. So we'd want no less than a 250 by 250 concrete column. Our concrete wall would be 4.2 divided by 25, or 168. We would round up to the nearest 50 millimeter increment, and I've said we wouldn't use anything less than 200 millimeters anyway. What if this was the ground floor column of a 45-story building? You've been in those buildings. Those columns are gigantic. They are not 12 inches by 12 inches. So this is where you understanding the context is really important. These sizing guidelines have no context. They're just assuming things are relatively normal and not that exciting. If you knew that this was the ground floor of a 45-story building, you'd probably want to draw something a whole heck of a lot bigger than 250 by 250. How much? Couldn't tell you, but probably something much bigger. Masonry. So masonry, we're talking about brick or block. They usually, and I'm more specifically talking about block here. You normally get it in, so this is the thing that looks like, draw you a really bad drawing here. This is why I am not an architect. It looks something like this, where this distance right here is the width, and the length comes in kind of different standard lengths. They have holes in it that we put rebar in, and we can grout it where we need it to. 190 is the most common. You'll often hear it referred to as 8-inch block. They leave 10 millimeters shy everywhere to take up the grout. If it's brick and we're building up a wall, we would have more than one withe, and they'd be, every now and then there'd be one turned, binding those two withes together. So what would the size of a wall and a partition be for a building with 4.2 story to story height? So if it's load bearing, I mean it's supporting a load, it's h divided by 20. If it's just a partition that's not going to bear any load and it just needs to be laterally braced into something else up at the top, it can be h divided by 36. So a load-bearing wall, we would want to use 240 block, and on the same project, for anything that's not load-bearing, we'd want to use 190 block. So what happens when it's the brick veneer? And this is a really good guideline because architects draw brick all over the place, not supported, mostly because it's not taught anywhere. Brick veneer, if it's starting at grade, can go up to 11 meters. Brick veneer, higher than that, needs to be supported at every story, usually with a steel angle somehow connected back to the main part of the building. Brick veneer is also laterally connected to the building, so that means so it can't kind of blow and move around every 600 millimeters. So kind of last overall sizing guideline I want to give you is about a cantilever. So when we're using the cantilever length, the rule of thumb would be half of whatever the beam rule of thumb you were using was. So if I have an 8-meter backspan and a 4-meter cantilever, we know that if it was a steel beam, that 8 meters would be L divided by 200. If it was a girder, it was L divided by 15. If it was a concrete beam, it would be L divided by 16. And let's say weirdly it's a concrete slab. That would be a really thick slab. But let's just talk about it as a kind of a loose application. Well, we would use half of the length, not the half of this length, but the half of this length. We would change our sizing guidelines and cut it in half. You could do it either way. We would change our sizing guidelines and cut them in half. So we take the length of our cantilever and divide it by half of the sizing guideline. So you can see 8-meter backspan, 4-meter cantilever, we get the same depth. If these weren't exactly half of each other, we would not get the same numbers here. You want to make sure if this is one continuous beam that you're going to use the worst case or the deeper one. If this was a 5-meter cantilever, all of these numbers would have gone up and they would have governed the depth of our overall number. If this was 9 meters and this was 4 meters, all of these numbers would have gone up and our backspan would have governed our overall. I hear noise coming out of your phone. Oh, he's got headphones in. So last slide, takeaway tips. Sizing guidelines will help with preliminary sizing. They're not perfect. You've even seen in these slides that there was talking points that were like, well, this would be slightly different and this would be slightly that. I've tried to be very crystal clear in the assignment questions I gave you. These aren't meant to be difficult. They're meant to be used as a place to start where you know what's weird beyond that. So if I'm giving it to you, it's normal, unless I tell you very explicitly it's something weird. And so you should understand your constraints. Joists for wood are going to be at 16 inches on center. Open web steel joists and purlins are going to be at 2 meters on center. And sizing guidelines, these are going to be something that you guys are going to want with you on your desk, when you're still working at 100, because you're going to be architects. You're going to need to work until you're 100, let's face it. So you're going to want those with you because they're going to be very helpful throughout your career. Engineers tend to forget about them because we start to rely on the math too much, I think. But the sizing guidelines can be really helpful. So remember, a couple of the slides are going to have slightly different numbers from what I showed going through this presentation. So make sure you have the correct one open in front of you because I'm going to go back and make those few updates to the lecture slides so that you have the best information in front of you. Rather than go back and re-record for a few small things, take a look at those lecture slides and kind of look at them in tandem together. You might find that very helpful. Okay, see you guys next week when we start to talk about loading.